When determining maximum overcurrent protection for refrigeration compressors, there are two amperage listings to consider: firstly, the service guide table, and secondly, the performance base table. The performance base table amperages are often significantly lower, sometimes almost 50% less than those found in the service guide table. Traditionally, the higher amperages in the service guide table have been used for calculating maximum overcurrent protection. The question arises, can the performance-based tables be used instead? The answer is yes, but with certain conditions. Operating conditions are paramount. The performance-based table should only be used when the refrigeration compressor operates within the specified coolant temperature range and adheres to other operating conditions outlined in the manufacturer's specifications. A safety margin is crucial. It is essential to incorporate an adequate safety margin to account for potential variations in operating conditions, such as unexpectedly higher coolant temperatures or unusual loads. Always ensure code compliance. The calculated maximum overcurrent protection must comply with all applicable electrical codes and standards, such as those set forth by the National Electrical Code, often referred to as NEC, or the International Electrotechnical Commission, known as IEC. Here is a step-by-step procedure. 1. Refer to the performance-based table specific to the compressor model and its operating conditions. 2. Use the lower amperage value from the table as the basis for calculating the maximum overcurrent protection. 3. Add a suitable safety margin to this calculated value. 4. The resulting value should be used as the maximum overcurrent protection setting for the compressor. Several considerations should be taken into account. The service guide table amperages typically represent the worst-case maximum current draw. In contrast, the performance-based table amperages reflect more typical operating conditions. If the compressor is expected to operate consistently at or near its maximum capacity, it is advisable to use the service guide table amperages to ensure adequate protection. Always consult the manufacturer's documentation for the most accurate and up-to-date information. It is also highly recommended to consult with a qualified electrician to ensure that the appropriate maximum overcurrent protection is selected and properly installed. To further elaborate on the selection process, let's delve deeper into the differences between the service guide table and the performance-based table. The service guide table provides a conservative estimate of the compressor's current draw under virtually all operating conditions. This table is designed to account for factors such as voltage fluctuations, high ambient temperatures, and prolonged periods of heavy load. Therefore, using the service guide table ensures that the overcurrent protection device will trip before the compressor is damaged, even under the most demanding circumstances. On the other hand, the performance-based table offers a more precise estimate of the compressor's current draw under specific operating conditions. This table takes into account factors such as the coolant temperature, the suction pressure, and the discharge pressure. By using the performance-based table, it is possible to select an overcurrent protection device that is more closely matched to the compressor's actual current draw. This can help to prevent nuisance tripping, which can occur when the overcurrent protection device is too sensitive. However, it is important to note that the performance-based table should only be used when the compressor is operating within the specified conditions. If the operating conditions deviate from those specified in the table, then the service guide table should be used instead. When calculating the maximum overcurrent protection using the performance-based table, it is crucial to add an appropriate safety margin. The safety margin should be large enough to account for any unexpected variations in the operating conditions. A general rule of thumb is to add at least 15 to 25% to the calculated value. For example, if the performance-based table indicates a current draw of 10 amps, then the maximum overcurrent protection should be set to at least 11.5 amps to 12.5 amps. In addition to the safety margin, it is also important to consider the type of overcurrent protection device that is being used. There are two main types of overcurrent protection devices, namely fuses and circuit breakers. Fuses are designed to melt and break the circuit when the current exceeds a certain level. Circuit breakers are designed to trip and open the circuit when the current exceeds a certain level. Fuses are generally more accurate than circuit breakers, but they must be replaced after they have tripped. Circuit breakers can be reset after they have tripped, but they may not be as accurate as fuses. The choice between fuses and circuit breakers depends on the specific application. For example, fuses may be preferred for applications where accuracy is critical, such as protecting sensitive electronic equipment. Circuit breakers may be preferred for applications where convenience is important, such as protecting lighting circuits. Regardless of the type of overcurrent protection device that is used, it is important to ensure that it is properly sized and installed. The overcurrent protection device should be sized to protect the compressor from damage, but it should not be so large that it allows the compressor to operate at an unsafe level. The overcurrent protection device should be installed in accordance with all applicable electrical codes and standards. It is also important to periodically inspect the overcurrent protection device to ensure that it is functioning properly. If the overcurrent protection device trips frequently, it may indicate that there is a problem with the compressor or the electrical circuit. In this case, it is important to consult with a qualified electrician to diagnose and repair the problem. Now let's discuss specific examples to illustrate how to apply these principles. Suppose a refrigeration compressor has a rated voltage of 230 volts and a performance base table amperage of 8 amps under specific operating conditions. The service guide table lists the amperage as 12 amps. The compressor is expected to operate consistently within the conditions specified in the performance base table. Firstly, we start with the performance base table amperage of 8 amps. Secondly, we add a safety margin of, say, 20%. This means 8 amps times 1.20 equals 9.6 amps. Thirdly, we need to select an overcurrent protection device that is rated slightly above 9.6 amps. A standard 10 amp circuit breaker or fuse would likely be suitable. Fourthly, we verify that this 10 amp protection complies with the relevant electrical codes and standards. NEC Article 440 provides specific guidelines for hermetic refrigerant motor compressors. We consult Article 440.22, which addresses the rating and setting for motor compressor overcurrent protection. The code states that the overcurrent protection shall be capable of carrying the starting current of the motor. For a hermetic refrigerant motor compressor, the overcurrent protection shall not exceed 175% of the motor's rated load current or branch circuit selection current, whichever is greater. In this example, 175% of 8 amps is 14 amps, so our selected 10 amp protection falls within the code's requirements. Now consider a different scenario. The same compressor is now expected to operate under more variable conditions, potentially experiencing higher coolant temperatures or increased loads. In this case, it would be more prudent to use the service guide table amperage of 12 amps. Firstly, we start with the service guide table amperage of 12 amps. Secondly, we add a safety margin of 20%. This means 12 amps times 1.20 equals 14.4 amps. Thirdly, we select an overcurrent protection device rated slightly above 14.4 amps. A 15 amp circuit breaker or fuse would be a suitable choice. Fourthly, we again verify compliance with NEC Article 440. In this instance, 175% of 12 amps is 21 amps, so the 15 amp protection still meets the code requirements. It is also important to consider the wire size used in the circuit. The wire must be sized to carry the load current plus any applicable safety margins. NEC Table 310.15b16 provides ampacity ratings for various wire sizes based on insulation type and temperature rating. For example, if using copper wire with type THHN insulation rated at 90 degrees Celsius, a 14 American wire gauge or wire is typically rated for 20 amps. A 12 AWG wire is rated for 25 amps. Therefore, in our first scenario with a 10 amp overcurrent protection, a 14 AWG wire would be acceptable. In the second scenario with a 15 amp overcurrent protection, a 12 AWG wire would be required. Additionally, consider the ambient temperature in which the compressor and wiring are located. If the ambient temperature is high, the ampacity of the wire may need to be derated. NEC Table 310.15b2 provides correction factors for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. For instance, if the ambient temperature is 40 degrees Celsius, the ampacity of a THHN wire may need to be reduced by approximately 8%. Another factor to consider is the voltage drop in the circuit. Voltage drop occurs when the voltage at the load is less than the voltage at the source. Excessive voltage drop can cause the compressor to operate inefficiently and can even damage the motor. The NEC recommends limiting the voltage drop to no more than 3% for branch circuits. To calculate the voltage drop, you need to know the length of the wire, the current flowing through the wire, and the resistance of the wire. Online voltage drop calculators are available to simplify this calculation. In addition to the NEC, other standards may apply depending on the specific application and location. For example, Underwriters Laboratories, known as UL, standards may be relevant for the listing and certification of the compressor and its components. Local building codes may also impose additional requirements. Consulting with a qualified electrician is essential to ensure that all applicable codes and standards are met. In summary, selecting the appropriate maximum overcurrent protection for a refrigeration compressor requires careful consideration of several factors, including the operating conditions, the manufacturer's specifications, the electrical codes and standards, the wire size, and the ambient temperature. Using the performance-based table can be advantageous when the operating conditions are well defined and consistent, but it is crucial to add an adequate safety margin and to verify compliance with all applicable requirements. When in doubt, it is always best to err on the side of caution and to consult with a qualified electrician. It is also important to consider the motor's locked rotor amps, also known as LRA. This is the amount of current the motor draws when it first starts. The overcurrent protection device must be able to withstand this inrush current without tripping. The LRA is typically listed on the motor's nameplate. The NEC provides guidelines for sizing the overcurrent protection device based on the LRA. For example, NEC Article 430.52 specifies the maximum rating or setting for motor branch circuit short circuit and ground fault protection. The type of overcurrent protection device, such as an inverse timed circuit breaker or a dual element fuse, affects the allowable percentage of the LRA. The specific percentages are detailed in NEC Table 430.52. Furthermore, consider the type of motor starter used with the compressor. A motor starter is a device that controls the starting and stopping of the motor. Different types of motor starters have different inrush current characteristics. For example, a reduced voltage starter, such as an autotransformer starter or a part winding starter, reduces the inrush current compared to a full voltage starter. If a reduced voltage starter is used, the overcurrent protection device can be sized smaller than if a full voltage starter is used. The manufacturer's documentation for the motor starter will provide guidance on selecting the appropriate overcurrent protection. Regular maintenance and inspection of the compressor and its electrical components are essential for ensuring safe and reliable operation. This includes checking the overcurrent protection device to ensure that it is functioning properly, inspecting the wiring for any signs of damage, and verifying that all connections are tight. A qualified electrician should perform these inspections on a regular basis. In addition to overcurrent protection, other types of protection may be required for the compressor, such as undervoltage protection and phase loss protection. Undervoltage protection protects the motor from damage due to low voltage. Phase loss protection protects the motor from damage due to a loss of one or more phases of the power supply. These types of protection can be provided by a motor protection relay. A motor protection relay is a device that monitors various parameters of the motor and provides protection against various types of faults. The motor protection relay can be programmed to trip the motor starter if any of these faults occur. When selecting a motor protection relay, it is important to consider the specific needs of the compressor and the operating environment. The motor protection relay should be selected to provide adequate protection against all potential faults. Finally, remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest requirements and to consult with a qualified electrician to ensure that all electrical work is performed safely and in accordance with the applicable codes. These detailed considerations will assist in ensuring a safe and efficient refrigeration compressor installation.